Hi, today I'm back on the EEPROM replacement, and the focus today is to try to get some progress towards getting the data off of this, my Serial EEPROM, and onto this, an SRAM. I want to do that during reset of the circuit. Now, I don't want to go directly to Breadboard with that. I want to emulate it before I actually start committing anything into hardware. So I'm back on the emulator today working on that. And I've got a few things that I've got to work through in order to be able to do that. One of the things I need to be able to do is to identify which EEPROM I'm going to read for each control ROM on the emulator. I want to be able to use the control ROM images themselves in order to drive the logic. And so I've got some building to do for that. I've got to be able to emulate both the SRAM and the EEPROM. Plus, I've got a whole suite of things I need to do for the reset circuitry and holding the circuit in reset while a copy is taking place from this to this. Let's get into it. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. Okay, here's the emulator as I left it. In the upper right-hand corner here, there is a test harness where I actually take the place of the control logic. Eventually, I need to be able to load the control ROMs off of disk after they've been built so that the emulator faithfully represents what I have put together for the ROMs in real life. For me to be able to do that, I want to be able to set those up independently. That way, if I have a copy of ROMs that I want to save off and revert back to as I'm continuing my development, I want to be able to reset this easy enough so that it is reading and using the control ROMs that I really want. So what I really want to do is I want to add settings to the emulator so that I can set up exactly which control ROMs I'm going to be using. Now I am to understand that Qt6 has a settings class which is really good at maintaining synchronization with the file on disk. That way, if you make a change in the settings object, it will update that onto disk immediately. And so I want to pull that out and start learning a little bit about that, figure out exactly what I need to do. There is going to be a change to the look of the emulator. Not exactly sure how that's going to come together yet. And there may be some pretty significant changes because I do need to change my background widget in order to allow a menu to be added. So we'll see how that works. Let me get some changes done and I will come back and let you see what that looks like. Okay, here it is. Now on the bottom, I added a status bar. On the top, I added a menu. Other than that, there's really no major change to the UI. I did add a quit option here, and then I can get into the settings. And this location is stored in a configuration file location. You can select which directory you want to use, and on clicking OK, that gets saved off into that configuration file. So if I come out here to my config folder, I've used ARIJUS and then the 16-bit computer from scratch emulator. You can see that this is where that configuration setting is stored. This now tees up the emulator to be able to read the control ROMs from that folder and load them up into memory. Now the control ROMs, as in EEPROM, are going to be emulated just as a file. And then I need to emulate the read instruction where I shift out the individual bits from the EEPROM so that they can be moved into the actual SRAM. So that'll be the next step here, is to create that EEPROM so that I can actually load up the contents of the control ROM from disk and start shifting that out properly. Let me get that done and I'll be back to share that code with you. There won't be much in the user interface. Okay, so There's really not much I can show other than demonstrating the code that I wrote. What I've got is I've got my folder here where my control ROMs are going to be located, and you can see I've got them here ordered from 0 through B, so I've got 12 control ROMs. Now I did change the numbering of them in order to make sure that I had room for a total of 16 just in case I needed them. If I go more than that, I'm not exactly sure what I'm going to do. Now, when I launch the emulator, there are no error messages that pop up down here, but if I happen to change my settings so that it points to a different folder, and you can see that it's now reloaded a different folder into the settings. When I launch it a second time, there are a number of error messages that pop up here to indicate that it's not able to load the EEPROM. But if I change it back, that did not launch properly. Why did it not launch properly? Because it didn't commit the change. All right, having changed it back, if I launch it again, you can see there are no error messages. All right, so I know I've got the EEPROMs read off of disk and placed into RAM memory for the emulator. Now this is heap memory. The memory of the emulator, not the emulated memory of the emulator. Yeah, that makes a lot of sense. But I do have the EEPROMs loaded from disk and stored in the Serial SPI EEPROM. What I need to now do is I need to get those out and into an emulated SRAM IC. Now I can't demonstrate much more than this now until I get that done. But what I can show you is the code. So what I chose to do is here's the pins and everything that I've got implemented, and I'm only implementing read. I'm not implementing write or any of the other features of the EEPROM. Just read, because that's all I need for this. But I've got a matrix of the commands that could be executed, or portions of the commands that could be executed, that I can bitwise or with the bits of the command, since I'm transferring 1 bit at a time, and bitwise ORed with the clock state. And that gives me a single 32-bit value that I can then use in a finite state machine to indicate exactly what state the EEPROM is in. And that's exactly what I did. So the constructor just reads from disk. If it is unable to read from disk, it reports the fact that it's not able to open the file. But when I process a clock signal, this switch statement here determines what the current state is, and then will update the state based on what happens next. All right, so if you're not familiar with what a finite state machine is, basically it has some number of states, and the state will change based on some number of actions that can be performed at any given state. What does that mean to us? Well, my inputs are obviously a clock transition from high to low, from low to high. I can also disable the chip select. So anytime my chip select changes state, I reset the state back to its initial state. Those are the two inputs that really can drive what state this is in. So when I am shifting in an instruction, I do one thing. When the clock is high, when I'm shifting in an instruction and the clock is low, I do another thing. And that thing is to advance the bit to the next bit. So that now puts me, when the clock goes high, at this state. And then when the clock goes low, at this state, which advances the state. What that allows me to do is put together a rather complicated series of events that need to take place, but keep it relatively simple once you realize that you're dealing with this kind of a state transition from one state to another. And that's what this is. This is just a massive switch statement. And as I go from receiving an instruction, I verify the instruction is actually a read instruction, and then I go say I'm going to get the most significant byte of the address. That's the next thing that comes in. The most significant bit of the most significant byte is ignored. There's only 15 bits in the address, so we do nothing with it. When we get the next bit, we shift that onto the address. Once we get to the end of the most significant byte, my next state becomes reading the least significant byte. and it goes through that. And once we get to the end of the least significant byte, then I set my mode to be reading. In other words, I am outputting data from the EEPROM such that the host program can read it, or host hardware can read it. The byte that I'm going to transition out is the contents of the EEPROM at the address that we just loaded, and I'm going to start shifting bit 0. Now, unfortunately, or fortunately, however you want to look at that, bit 0 is the first bit, but it always goes most significant bit first. So as I'm shifting out these bits, I start with one shifted up 7 bits, then one shifted up 6 bits, then one shifted up 5 bits as I walk my way down that byte. Once I have shifted out the entire byte, I increment the address, make sure that I'm taking the least significant 15 bits of that address. Recall the EEPROM is 32K bytes long, so I only need 15 bits to address that. I go get the next byte, I set the bit back to 0, and I am stuck in this loop here, outputting data, just like the datasheet says, until my chip select goes high. Okay, so next up I've got to get the parallel RAM set up so that I can copy the data from the EEPROM into the RAM. It's another foundational IC that we need to get built into the emulator so that we can start talking about exactly how we want to do this shifting and move this data from the serial EEPROM into the RAM so that it's available. Let me work on that code and I'll come back and present the changes. All right, the RAM has been built for the emulator. Forgive me, my 3D printer is going in the background. You might pick up some of that noise. I apologize for that. This is the IC that I've got in AS6C62256. I probably could shorten that to just a 62256, but I'll leave it the way it is. The constructor takes, optionally, a pointer to the host ROM, the SPI ROM, so that it can perform some sanity checks if I choose to go down that path. And in the case of the control logic, I'm going to implement that. And this is an optional check here. If I don't pass in anything to check against, then obviously it can be used as RAM and might get corrupted or might not, what have you. But if I do have a ROM image I can compare against, I'm going to do that with every clock cycle. Yeah, that's a lot of CPU cycles to compare 32K of memory, but I believe it's going to be worth it in the early debugging stages. So each one of the pins can be updated, and I then have a function called update all, which takes care of processing all the inputs to the outputs. The data pins on the RAM are bidirectional, so this is new, and I have to pay attention to this now. To make sure that when I set inputs externally, they persist. If I update internally, pushing data out, that I get everything updated properly. And I don't want the external updates to the input data pins to turn around and become outputs where I'm signaling data changes. That'll end up just being a messy situation, even in the emulator. Now I've got this slot here for processing the sanity check, which I will at least start off using. And then for the actual implementation, my constructor sets the initial state for all the pins, and then my trigger first updates is to get everything in sync after getting them quote unquote connected in the code. Now, some states are going to be required to output high impedance, and I do that instead of outputting the contents of the data pin. I output just simply a Z state on each of the output pins without changing the pin state itself. And that's how I'm intending to preserve that state. And then my update all function, there's really a handful of situations, and I update the inputs and outputs based on that situation. A couple of them will output high impedance. There is a write mode, and I do have that. I will use that with the SRAM. So I calculate what the byte is going to be, I calculate what the address is going to be, and perform that update. But I don't update or push out any of the results because it's an input bidirectional. On the other hand, if I'm in read mode, I will have an address, I will have the contents of RAM at that particular point, and I will turn around and output those out onto the data pins, and then I just reuse this trigger first updates in order to perform all the signals appropriately. It's a relatively simple IC, honestly, but I do not yet have the ability to test this because I have no way of actually getting anything loaded into it. And so that's what I want to do now, is I want to spend some time talking about exactly what this design is going to look like in order to read the data from the ROM serially and push it onto the RAM in parallel. Let's pull that together. Okay, let me start off here by saying that I have kind of a plan here, but not really. And I really am not quite sure how this is going to turn out. I only hear it in my head about half a second before I speak it, so we're going to work on this together. I also want to mention that I've been watching a bit of Jerry Walker lately on YouTube. If you haven't seen his videos, go check them out. There's an elegance and beauty in the simplicity of his designs that I can only hope to imitate. I'm going to make an effort to imitate that here, but I will not likely be very successful. Let's start with a simple question first. Adam, how are you going to get serial data onto a parallel RAM IC? And the quick answer to that is to use a 74HC165. Okay, I actually looked before even recording this segment, and I still managed to get the two ICs confused. The IC I need to use here is a 74HC164. That's going to shift bits in and provide a byte out in parallel. I got a good portion of this segment recorded before I realized my mistake. So I'm going to voice over here to correct it and update the graphics. Shift register, which is going to take a serial input and organize that into 8 parallel outputs so that I can turn around and load that onto the RAM. The next thing I'm going to need to be able to do is count off 8 bits being shifted out of the ROM into the shift register, such that when I get all 8 bits, I can then trigger the RAM to latch that value into the correct address. Now for that, I'll use the 74HC193. We've used that many times before. It's an up-down counter. Speaking of addresses, I need to be able to count up all 32K of address bytes in the RAM so that I can load them sequentially. For that, I will use 4 of the 74HC193 up-down counters. I need 15 bits for that, so one of those bits is going to go unused for now. The last thing I know I need to do that I actually have a plan for is the serial ROM needs 3 bytes worth of data in order to start sending its contents out. It needs a read command shifted in. It needs 16 bits worth of address shifted in. Now only 15 are used, but it requires that 16th bit. And for that, I'm going to use a 74HC165, which is a parallel load shift register. So with the 74HC165, I am able to preload a value onto that register before it starts shifting out. And that then allows me to preload that read command and then start shifting from there. Now, once a bit is shifted out of the 74HC165, it makes room for a new bit to be shifted back in. If I shift in a logic low or a binary 0, ultimately I could easily pass the address 0 onto the serial ROM as its starting address, and then it reads in increments from there. Nothing that you see here, though, has anything related to orchestration built into it yet. It just shows how and where data is going to be moved around, but it doesn't indicate the timing. The first thing I want to talk about here are some of the control signals I'm going to need for each of these ICs to make sure that everything is kept in sync. Not necessarily how I'm going to shape those or determine the timing of them, but I want to get them identified so that I don't miss anything. The serial ROM has 4 control signals I need to figure out. These are chip select, write protect, hold, and then the serial clock. The 74HC164 IC has 2. These are clear and the clock. The 74HC165 has 3 signals I'm concerned with. The first one is a signal that indicates whether we're shifting or loading. The second one is a clock, and the third is a clock inhibit. 74HC193, once again, we're familiar with. It's got 4 signals that we're interested in here. Clear and load, and then count up and count down. Now, count up and count down are not just signals, they're tied to the clock. And I'm going to ignore borrow out and carry out for the moment. They'll be used in the set of 4 for the address, but not on the single IC for counting the number of bits. And I'm going to reserve the right to wire up those 2 groups differently and have those signals shaped differently, so I'm going to keep them separate in the diagram. The last IC here is the RAM IC, the AS6C62256. That has 3 signals of interest. One is output enable, one is write enable, and one is chip enable. Finally, for my inputs into this circuit, I will have a reset signal, which has been previously active low, but I want to change that to be active high. I've got a note to myself that I need to make that change. And I'm going to design this circuit as if it is active high. And then I'm going to need some form of a clock. Now, for the emulator and for my build, the emulator has a ridiculously slow clock, and it's going to take, 3 days to copy the data. So I'm going to come up with something that's a little bit faster for the emulator. But for the build, I'm likely to use a high-speed clock that I've got tucked into the build somewhere. So I'm not exactly certain how I want to do that, but I know that I need a clock for an input. The output of the circuit is going to be a reset hold signal, meaning that it is still in the process of resetting and copying that data from the Serial EEPROM onto the RAM. This one is going to be an active low signal because the ICs that I'm going to use to drive that are going to be an open drain in CMOS, meaning that the 2 states are either low or it's high impedance. Okay, before we get into a deep dive of each of these signals, there are a few of them I can say with reasonable certainty that I'm not going to use. On the serial ROM, the write protect is always going to be set, so that's going to be pulled low. The hold signal I'm not going to use, that'll be pulled high. The clock inhibit on the 74HC165 is never going to be used, so that can remain low. On the 74HC193 ICs for the memory address, I'm not going to use low, that can remain high. And I'm not going to count down, so that can also remain high. Okay, as we move away from the trivial things and into the more detailed stuff, it's important to understand that this circuit is going to have 3 states that it can operate in. The first is in reset, meaning the voltage supervisor has detected a problem, or I am pressing the reset button and the circuit is actually in a reset state. That reset signal will be high, and that will happen independent of the clock. So anything that we do bringing it in or out of reset needs to be coordinated with the clock in this circuit. The second state is going to be while we are copying data or in reset hold. And that's when that signal is held low, meaning that we cannot allow the computer to do anything because we are still copying. And finally, the last state is normal operation, when we are completed with copying and are ready for the computer to actually start working. The last thing to talk about before we get into some of the messy details is we need to bound the start of reset with the end of reset hold when we release the circuit to start running again. Now this hold needs to start with the beginning of the reset signal going high and then end when we can release the rest of the computer with the reset hold going to high impedance. The best way to do that is with a set reset latch and then pipe that output through something that converts a high signal to a high impedance. And I've got an IC for that. I've got an AND gate. I can push it through in order to do that. I may need some additional conditions, and that's why I chose to use an AND gate so I can shape that properly. The last thing I need in order to manage these signals is some way to get the circuit into reset and hold it in reset until a clock boundary. Well, for that, I'm going to use a D-type latch with set and clear pins on it. The 74HC74 provides this. And so what I'll do is I'll tie the reset signal into the clear pin coming in and also to the data pin. And that will set it up so that on the clock transition low to high, it will then latch the reset signal. That way the circuit only changes on a clock boundary, keeping the synchronization that's required. So now I can simplify the conditions table. I have just a few pins that I can query in order to determine exactly what state the circuit is in. The clear signal for the 74HC193 ICs is going to be simply the inverted QR signal. The 74HC164 IC has a clear signal as well. That one is going to be the QR signal. The 74HC165 has a shift and load signal. We want the load signal to be active while we are in reset, so that will end up being the QR signal. For the serial ROM, we want chip select to be low only after reset is complete, but while the copying is still taking place. Reset is complete when the QR signal comes high. Copying is taking place with the QC signal is high. Now, the QC signal is also high during reset, so we can't use that just independently. But if we AND those two signals together, the result will come high after the reset is complete and that state is latched properly, and while copying is still taking place. Now, chip select is an active low signal, so if we invert that using a NAND gate instead of an AND gate, that presents the signal properly to that pin. For the ROM side of the circuit, the last thing to talk about is the clock. Now, I only want the clock to be a factor while we're copying data. So that is while the circuit is in reset and while we are copying data. So that's going to be the QC signal ANDed with the clock. Now, once QC goes low, that should then cut the clock off from the ROM side of the circuit, making the ROM no longer a factor anymore. Moving over to the RAM side of the circuit, let's start with the easy one. The output is only going to be available when we are done copying from ROM to RAM. So the QC signal is high when we are copying and low when we are not, so I can drop that in place for output enable. The write enable on the RAM also needs to follow the clock so that the data is actually latched or committed on the rising edge of the clock signal. We only want that happening when we're copying data. And so that's going to look like the clock signal for the 74HC165. Chip enable is a bit of a thorn in my side. For reads, it can remain low, and I'm limited by an address transition time during which the data is not valid. But for writes, it must come high while an address is being changed. It notes that in the data sheet related to the write cycle timing. Now, it's never a good thing to ignore the data sheet. So when we are copying data, I need the chip enable and write enable to have the same shape and the same timing. But when we're done writing and we're in normal operation, the chip enable can remain low. And of course, this is where it all gets confusing. My write enable signal is actually wrong. Okay, so let's take a look at a truth table for this. For my write enable signal, which is an active low signal, when QC is low, meaning that we're no longer copying data, I need the result of that to be high. I'm no longer writing to the RAM. When QC is high, I need it to follow the clock. In other words, when the clock is low, the signal is low. When the clock is high, the signal is high. Now, that's a difficult piece to wire up. But if I invert QC and instead look at the inverted output of QC, this now turns into an OR gate. Now, if I do the same exercise with chip enable and I follow the conditions that I want leading into this, I've got just a simple AND gate here. And even at that, chip enable and write enable are not yet correct. We'll circle back around to that as well. Let's move on to the counter that counts the number of bits in a byte to signal when it's the proper time to latch the byte into RAM. Now, I want to be able to count 8 bits. What I want to do is I'm going to load up the value 7 and count down to 0. So that means my count up is going to remain high. My count down is going to be tied to the clock, and my load value is going to be set to be 7 in binary. Since I'm loading a value, clear is no longer appropriate. That should be tied low, but my load signal now is a little bit more complicated. I need to load asynchronously while we are in reset, and then at the same time load every time that we have a borrow. Time for another truth table. Now, the conditions here related to the load are going to be dependent on the currently being resetting and the borrow out flag coming off of this counter. And when I put those in a matrix in a truth table, this shows up as an AND gate. Now, the counters for the address are very different in nature. I need to count up, and that is based on the requirement that the ROM is incrementing its address. I need to make sure that the RAM increments its address as well. So we'll tie the clock to the up count pin, and we will tie the down count pin high. I'm not going to clear it on reset, but I'm going to load a value. Now, the reason I need to load a value is I need to pass off 32K bytes of data from the ROM to the RAM. Plus, I need to send in 3 additional bytes of command and address data. So there's more than just in hex 7FFF bytes that I'm moving. And so I'm going to set that initial value on reset to include those 3 bytes. Clear won't be used, so I will tie that low. Now, once the address counter rolls over for all 16 bits, notice I chose my load value carefully such that after the 3 bytes plus the 32K, the carry out flag will go low, and that will be tied to the reset pin of the set reset latch for copying. That will take me out of copying mode and put me into normal run mode. You know, I'd like to think that this is complete, but in reality, there are some issues still here to be sorted out. First of all, on the address counters, it is counting with every single clock, and that is incorrect. We only should be counting based on the borrow out of the 8-bit counter. So when that rolls to 0, only then should we increment to the next byte. The next thing is the address is going to be driven from multiple places. So we need to be able to separate the counters, the 74 HC193 counters for the address, from the instruction, which is also going to drive that address. For that, I'm going to introduce a couple of 74 HC157 multiplexers. These are 2-to-1 input multiplexers, and I will need 4 of those. That will then allow me to select back and forth between the counter ICs and the instruction driving that address based on what's going on with QC. For chip enable, I now have 3 conditions that I need to take into account in order to determine its value. Now again, chip enable is active low, and I've organized the table such that only 1 bit ever changes as we go from one row to the next. Makes it a little bit easier for looking for patterns and consolidating. So I can do this by comparing 2 conditions. Either my QC is high and my borrow out is high. In that case, the clock is irrelevant. Or if QC is high and borrow out is low and the clock is high, then that is set. Then my chip enable is brought high. Otherwise, that chip enable is low. Write enable is very similar, except I do not want to be able to write when I am not copying data. So as long as that QC is low, I want write enable to be high. Remember, write enable is an active low signal. Okay, well, I feel reasonably comfortable with this design. There are going to be some challenges with it. I am not totally certain that the shifting in and out with the Serial EEPROM and the shift registers if the timing of that is going to work out properly. I'm going to have to pay really close attention to that. Also, I have to pay close attention to the counters. The reset at certain points, I've got to make sure that those intervals are accurate and I actually get the correct number of counts associated with them. Also, the emulator is almost guaranteed to work or not work. There's one way to hedge my bet there. The way the emulator is architected, there are no timing issues. Ultimately, things happen sequentially, and there's nothing that takes into account the fact that there may be some delay in one circuit or one IC that is longer or shorter than the delay in another IC. And so I may have success in the emulator that I won't see in hardware. So I'm going to try to get this done and committed to Breadboard as quickly as possible so that I can start kicking around and testing it. So I'm going to take on building the emulator pieces of this and trying to get to Breadboard, at least in part, in the next video. In the meantime, you've got the design up on the screen here. Let me know what you think of it. Let me know if you think that there's going to be any issues. I'll see you soon.